Anticipating that you experienced that dull opening, you would show up at another universe. There is already a connection between quantum computing and glaring flaws. In this informative video, we explore a vital and startling discovery made by the James Webb Space Telescope inside a black hole, explained by none other than Bill Nye the Science Guy. A black hole is a star so massive that even light cannot escape from it due to its immense gravity. The mysteries of black holes have puzzled specialists for a long time. However, thanks to surprising advancements, we've seen something truly stunning. The extremely large black hole consumes what could be, rather than 1 Earth per day. The startling and compelling first image of a black hole in space. Get ready yourself as we dive into the unbelievable nuances of this endless exposure and its potential implications for how we understand the universe. Stars toward the end of their lives, much greater and more massive than the Sun, run out of fuel and begin to collapse, as gravity crushes them. Black holes are fascinating to study. It was, in fact, a challenge to search for the first one, even though Einstein's theory of relativity predicted their existence. Unlike stars, black holes emit no light by themselves. They expand and rotate. These are the only quantifiable properties we have. Can black holes be seen? Attesting to their existence has only recently opened up. For a long time, definitive confirmation of black holes was lacking. The first black hole in Sagittarius X1 was observed in 1964, but it took over 30 years for experts like Stephen Hawking and Kip Thorne to agree on whether Sagittarius X1 was indeed a black hole. They became certain about their open investigation results but were cautious about the lack of conclusive revelations. Hawking and Thorne were almost 100% sure that Sagittarius X1 was a black hole in 1975, when a wager was made for the first time. By 1988, they were still 95% certain and held on until 1990 to confirm their belief when additional observations provided satisfactory confirmation. Initially, Sagittarius X1 was detected using 2 Geiger counters sent into space on a suborbital rocket. The device detected a signal pinpointed to a system 7,200 light-years away. The system highlighted a blue supergiant star orbiting another massive object emitting strong X-rays, which would make sense if it were a black hole. Since its discovery, much research has focused on Sagittarius X1, highlighting the fact that it is several times the mass of the Sun, making it the largest known stellar mass black hole found without gravitational waves. This discovery challenges long-held notions about black hole formation and the mass loss experienced by stars during their lifetimes. Sagittarius X1 breaks records in more ways than one. Its remarkable mass and the fastest spin speed of any black hole observed to date, approaching the speed of light, defy established patterns of black hole development. Although definitive evidence for black holes has only recently been found, it is increasingly clear that they are scattered everywhere in the universe. If scientists ultimately unravel all the mysteries of Sagittarius X1, the first of its kind, endless others still hold countless surprises. Under 2,000 light-years from Earth, specialists have found a dormant giant, Gaia BH3, the largest stellar mass black hole in the Milky Way, with a mass several times greater than that of our Sun. Despite being the second closest known black hole to Earth, Gaia BH3 remained undetected until recently. It was discovered accidentally while scientists from the European Space Agency examined data from the Gaia mission, which maps our galaxy in 3D. The discovery of this dormant black hole, which isn't actively drawing energy and material from a companion star, came as a complete surprise. Stellar mass black holes in our Milky Way have masses several times that of the Sun, with Sagittarius X1 holding the record at 15 times the Sun's mass. However, Gaia BH3, with a mass of 33 solar masses, is still small compared to all black holes. For example, the central supermassive black hole in our galaxy, Sagittarius A*, is 4 million times more powerful than the Sun. Gaia BH3, the second nearest black hole to Earth, follows only Gaia BH1, which is 1,500 light-years away and also has several times the mass of the Sun. Cosmologists now have more evidence to understand how stellar mass black holes form. These black holes result from the collapse of massive stars with lower concentrations of heavy metals. These metal-poor stars, made primarily of hydrogen and helium, are believed to undergo slower mass loss, leaving more material to form large black holes when they die. Using the James Webb Space Telescope, JWST, scientists have found an extremely red and massive black hole residing in the shadow of the early universe. As the universe expanded, this massive black hole took on a reddish hue and was created 700 million years after the Big Bang. The light reaching us is redshifted, indicating that a thick layer of gas and dust surrounds the black hole. Lucas P. Finnell and A.V. Curve of the Banan College Cosmology Group determined the black hole's mass using JWST data, finding it to be around 40 times the Sun's mass. This discovery stands out from the universe it inhabits, showing that the very massive black hole is quickly consuming gas and dust in the vicinity. Located about 12.9 billion light-years from Earth, this quasar was first identified by its red appearance. Quasars form when a large amount of material surrounds massive black holes, forming a disk of gas and dust that feeds the black hole. The massive gravitational influence of the black hole in this situation results in extreme temperatures, making it glow. The light produced by quasars can be so bright that it outshines all the stars in their surrounding galaxy. The JWST identified and confirmed this massive black hole as a small point of light due to the immense radiation it was emitting. Initially, the object was mistaken for a strange star-forming galaxy. However, color analysis confirmed the hypothesis of a very massive black hole. Its small size and immense mass stood out from other quasars observed in the early universe. This discovery was made possible by gravitational lensing, a phenomenon predicted by Einstein in 1915. Einstein's theory of general relativity suggests that massive objects distort the fabric of spacetime, forming a single entity called spacetime. This curvature creates gravity, and the larger the object, the more intense the distortion. The shape of spacetime also affects the light emitted by stars, bending it as it passes close to massive objects. This phenomenon, known as gravitational lensing, allows us to see distant objects that would otherwise be invisible. The JWST used this effect, supported by a galaxy group called SMXJ 7233-7327, to increase the brightness and visibility of the distant quasar. This natural magnifying effect allowed astronomers to study the black hole in unprecedented detail, despite its vast distance from Earth. The observations revealed that the black hole was not only massive but also extremely active. It was surrounded by a luminous accretion disk, hot gas and dust spiraling inward at incredible speeds, releasing massive amounts of energy as it fell into the black hole. These findings offer valuable insight into the early stages of galaxy and black hole formation. The discovery also raises new questions. How could such a massive black hole form so early in the universe's history, only 700 million years after the Big Bang? Traditional models suggest that black holes grow slowly over billions of years through steady accretion and mergers. Yet this one seemed to defy those expectations, suggesting that other, more rapid formation processes may have been at play. Some scientists now hypothesize that so-called direct collapse black holes, formed when massive primordial gas clouds collapsed directly into black holes without forming stars first, could explain the existence of such ancient, supermassive objects. Others are exploring the role of dark matter and exotic particles in accelerating black hole growth. Whatever the cause, this discovery has fundamentally shifted our understanding of the universe's early development. It emphasizes the importance of advanced instruments like the James Webb Space Telescope, which can peer farther into space and time than any previous observatory. As JWST continues to scan the skies, astronomers expect to uncover even more ancient black holes, each one potentially rewriting what we thought we knew about the cosmos. With every new image, spectrum, and data set, we move closer to answering one of the greatest questions of all: how did the universe, with all its complexity and wonder, truly begin? The brightness of red reveals distant galaxies. Quasars. This new information adds to the growing body of evidence that the early universe was populated with exceptionally large, dim openings, which can be millions or even billions of times as heavy as the Sun. Because this phenomenon has been observed in various large, dim openings in the early universe, it provides insight into the development of both the dim opening and the host galaxy, as well as the relationship between the two. The classic chicken or egg problem, however, on a cosmic scale, remains unresolved. Did the universe or the dim opening come first? How large were they? How did the first dim openings appear and evolve? Analysts might have found proof that microquasars, which are dim openings consuming companion stars, are enormous particle accelerators, producing unexplained high-energy galactic radiation. These enormous dim openings consume material from nearby, very large stars in binary systems, and some of the stellar matter is thrown out as relativistic jets, moving at unimaginable speeds. Microquasars are smaller versions of quasars, both energized by very large dim openings consuming nearby matter. In 1912, particles with high energy could strike Earth, with energies reaching 10 to the power of 20 electron volts, considerably more energetic than particles accelerated at the Large Hadron Collider, the world's most powerful atom smasher. The theory suggests that very large dim openings and microquasars are the universe's most extreme particle accelerators. However, Evidence of the acceleration of microquasar particles to such high energies has only recently been verified by means of the High-Energy Stereoscopic System, HESS. Analysts identified exceptionally high-energy gamma rays from the jets of the most powerful microquasar in the Milky Way, establishing a link between cosmic rays and microquasars. The microquasar SS433 produces high-energy gamma rays through its jets, which interact with surrounding matter, creating a shock front that moves electrons to extreme speeds. These gamma rays are a consequence of this interaction. SS433 was the first microquasar ever discovered, located at the center of the W50 supernova remnant, whimsically called the Manatee Cloud. SS433 has been the subject of extensive study for decades. The system consists of a white giant star and a dim opening about 10 to 15 times the Sun's mass. They orbit each other every 13 Earth days, with the star's outer layers being stripped by the dim opening's gravity. Some of this material forms an accretion disk around the dim opening, while other parts are ejected as jets traveling at 26% of the speed of light. These jets twist in a thin pattern, forming the W50 supernova remnant and making it appear to be a massive manatee. The jets fade over time but return in a repeating pattern, driven by the periodic motion of SS433. The jets from the dim opening also interact with the surrounding matter, creating a complex interaction between the dim opening and its environment. This behavior makes SS433 one of the most fascinating and enlightening objects in the study and application of microquasars in cosmic particle acceleration. Despite SS433 being the first identified microquasar, much remains unclear about how dim openings accelerate particles to such powerful energies and their broader impact on the universe. Scientists use various methods, including indirect measurements, to understand these giant phenomena. For example, dim openings can be observed through their interactions with neighboring stars and matter, as exemplified by the dramatic rise in the emission of X-rays as material is pulled into their gravitational grasp. This phenomenon is crucial in understanding dim openings and their role in the universe, revealing fundamental aspects of the evolution and behavior of these mysterious objects. In the realm of dim opening research, the new discovery of the most distant dim opening, an extraordinary 13.1 billion light-years away, has also expanded our understanding. This discovery belongs to these massive giants, made possible by the capabilities of the James Webb Space Telescope, JWST. It reveals a tremendously large dim opening formed under a billion years after the Big Bang. This early development challenges existing theories about dim opening formation and galaxy evolution. Observations suggest that these early dim openings may have played a significant part in the development of the structure of the universe by influencing the formation and development of the earliest galaxies. In addition to their role in galaxy formation, dim openings have been linked to powerful cosmic phenomena known as active galactic nuclei, AGN. AGNs are characterized by incredibly bright outflows from the areas around supermassive dim openings at the centers of galaxies. This outflow occurs when components from the surrounding accretion disk are heated to extreme temperatures as they spiral inward, emitting X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of dim openings and their influence on their host galaxies. These studies have shown that AGNs can significantly impact galaxy evolution by regulating star formation and distributing heavy elements throughout the galaxy. Recent advances in gravitational wave astronomy have provided a new way to test the properties of dim openings. The detection of gravitational waves from merging dim openings by observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, has opened a new frontier in understanding these elusive objects. These groundbreaking observations of gravitational waves have confirmed that dim openings, especially those in binary systems, can collide and merge, releasing vast amounts of energy in the form of ripples in spacetime. This not only supports Einstein's predictions from general relativity but also opens up a new method of probing the universe, allowing scientists to study dim openings that would otherwise be invisible through traditional electromagnetic observations. Moreover, gravitational wave data offers clues about the population, distribution, and mass of dim openings across cosmic history. For instance, some merging dim openings detected by LIGO and Virgo have masses that challenge current models of stellar evolution, suggesting that either exotic formation scenarios exist or our understanding of star death is incomplete. Another exciting development comes from multi-messenger astronomy, the combined observation of gravitational waves, light, and particles from the same cosmic event. When a gravitational wave event is matched with a visible light source, such as a gamma-ray burst or an optical flare, it allows scientists to pinpoint the event's location and study it in much greater detail. This technique has already revealed how certain types of dim openings may form through the collapse of massive stars or the merging of neutron stars. In addition, recent computational simulations and AI-driven modeling are enhancing our ability to predict the behavior of dim openings. By feeding vast datasets from telescopes and detectors into advanced algorithms, researchers can simulate the dynamic processes near dim openings, including accretion, jet formation, and magnetic field interactions, with unprecedented accuracy. One of the most intriguing frontiers remains the question of whether dim openings can serve as portals to new physics. Some theories propose that extreme conditions near a dim opening's event horizon, where gravity becomes infinitely strong, might offer insight into quantum gravity, information paradoxes, or even the nature of spacetime itself. Concepts such as Hawking radiation, which suggests that dim openings can slowly evaporate over time, are still being tested with data from high-energy telescopes and cosmic background studies. Furthermore, the potential link between dim openings and dark matter is under active investigation. Some hypotheses suggest that dim openings could interact with or even form from dense clumps of dark matter, offering a tantalizing glimpse into one of the universe's biggest mysteries. Understanding this relationship could help unlock the fundamental composition of the cosmos. Looking forward, the next generation of observatories, like the Einstein Telescope, the Laser Interferometer Space Antenna, LISA, and the Square Kilometer Array, will expand our observational reach and sensitivity. These instruments are expected to detect even fainter gravitational waves, map the earliest dim openings, and uncover the influence of these massive entities on the fabric of the universe. Ultimately, dim openings are not just astrophysical curiosities, they are keys to understanding how galaxies evolve, how matter behaves under extreme conditions, and possibly how the universe itself began and where it is headed.